Hello and welcome to Chapter 6. We have been studying series connected circuits in Chapter 5, and we did take a look at Kirchhoff's voltage law and how that helped us find the voltages around a circuit that is connected in series. So in this chapter, we're going to do something similar, but at the same time different. When we talked about parallel connected circuits. We're going to cover a lot of this chapter, and we're going to cover just about all the chapter except for a couple of sections at the end, as you will see. But this chapter and chapter 5 are really critical because everything else, everything else is building up, as you can see. But going forward, by the end of this chapter, you really have everything you really need to then understand some of the other more sophisticated methods for analyzing circuits. So please pay attention. I know it can be a little confusing once you start looking at circuits connected in parallel, because then in the next chapter we're going to mix that up. We're going to be looking at circuits connected. They can be connected seriously and in parallel within the same circuit. And so when we make that step forward, understanding specifically what's connected in series, what's connected in parallel, is really, really critical. So make sure you understand the differences, and as always, ask questions if you don't. So we're going to start by just simply understanding what we mean by parallel connected circuits. If you remember, when we study series connected resistances, one of the things we determined was that a series connected resistance connected to another resistance has one node in common, right? One single node in common. That's one of the things that makes series connected circuits easy to spot. They're only connected through one node. In the case of parallel connected circuits, the difference you will see is that in parallel connected circuits, two or more elements are connected in parallel if they have two nodes in common. Okay? 2 points or two nodes in common, not just one, but two. So that's one of the clues that you will see when you start, trying to figure out how they're connected. And you can see this in this figure here, right? Because now, as you can see, in this figure A, you have R1 and R2 have A in common and B in common, right? If you think in terms of the protoboard, right? This point A will be the same connecting point in the protoboard, and this point B will be the same node in the protoboard, right? So as you can see here, these two resistances share this node A and share this node B, so we can tell that those two resistances are in parallel. You can make the same argument with figure B, where R1 shares A with R2, and it also shares B with R2. So these two share the same two nodes, right? They share node A, and they also share node B. And you can see the difference now. In C, you can then start seeing the different ways of connecting circuits, right? Because now, if you look at R1 and R2 and R2 are obviously connected in series, and as you can see, they're only sharing one node, right? B is the only common node between R1 and R2. So R1 and R2, by what we already know, are connected in series. However, we know that you can combine R1 and R2 into a single resistance, right? So if you combine R1 and R2 into a single resistance, call it R4, then that R4 would be in parallel with R3. You notice? Because once you make this into a single resistance, then that single resistance will be sharing A with R3 and will be sharing C with R3, right? So that's how physically you can, or visually you can tell if resistors are connected in series or parallel. Another example here, R1, R2, and R3 also share the same node A, and they also share the same node B. So these three resistances are, we can say, they're connected in parallel. They're connecting to the same node at the bottom and to the same node at the top. Obviously, node A and node B are two different nodes, two different connecting points. And you can see also here different ways of connecting. Same idea here. If you connect everything to a point A and everything at the bottom to a point B, you're still connecting these three resistors to a common point A and to a common point B, because A is common to all the three resistances and B is common to all the three resistances. And in this figure C, it's exactly the same idea. Figures A, B, and C in this example are really the same circuit. It's just different ways of visualizing how they're connected, right? So make sure you understand that portion, that the connections to node A and B are just the same. It's just different ways of representing it or drawing them, okay? So just like we can combine resistors in series very easily by adding the resistors themselves, right, one by one, the way to combine resistors in parallel to get an equivalent resistance or a total resistance is by taking the reciprocal of the resistance. So what you will do is you will take the reciprocal of R1 plus the reciprocal of R2 plus the reciprocal of R3 and so forth, and then you will take the reciprocal of the total. Okay, that's the approach, that's the technique. You take the reciprocal of each individual resistance, and then that result, you take the reciprocal again to get the total resistance. Okay, if we talk in terms of conductances, if you remember, conductance is the reciprocal of the resistance, right? So for parallel connected resistances, the total conductance can be found by simply adding the individual conductances. Is sort of the opposite in the series connected case, if you remember, okay? So keep this formulas very much in mind going forward. So again, and the units are the same, right? Because it's the same resistance and the same conductance. Another way of generalizing that equation is, again, if you take the resistance of the individual resistors, right, like you see in this equation, and then you take the reciprocal of that, that will give you the total resistance, right? So that's what the equation represents. For example, in this figure 6.4, if you want to find the total resistance, looking into these two nodes, right? Obviously, first of all, you recognize that the two resistors are in parallel, right? So the 3 and the 6 are in parallel. So one way of finding the total conductance in this case, which is what they want, is by taking the individual conductance, right? So the individual conductance for this resistance is 1 over R, for this resistance is 1 over R1. So the conductance for this resistance is 0.333 Siemens. The conductance for this resistance is 1 over R2, or 0.167 Siemens. So the total conductance for this parallel connected resistance, it will be G1 plus G2, or 0.5 Siemens. Now, we could also have determined that another way, as we'll see in a minute. So finding the total resistance then is equivalent to now taking the reciprocal of the total conductance, right? So 1 over 0.5 Siemens is 2 ohms. So reviewing here, the total resistance for this circuit is found to be 2 Siemens. Now the way they found it is they found the individual conductances first. Okay, so they found the conductance for R1, which is 1 over R1. They found the conductance for R2, which is 1 over R2. And then since they are parallel, they add the two conductances together, which gave us the total conductance as 0.5 Siemens. To find the total resistance, we take the inverse, or the reciprocal, I should say, of 1 over the total conductance. And 1 over the total conductance give us 2 ohms as the total resistance, or the equivalent resistance for those two resistors in parallel. Now, we could also find the total resistance directly by using this equation if we wanted to. Okay? So what we'll have to do is, in this equation, we'll first take the reciprocal of R1, if you look in the denominator, add it to the reciprocal of R2, and then take the reciprocal of the result. Right? So doing that, we take the reciprocal of R1, 1 over 3, the reciprocal of R2, or we have 1 over 6, which is these two numbers. We add those two numbers, and then we take the reciprocal of the result, and gives us again the same answer, right? 2 ohms. So that's using this equation directly. Okay. So in this question it says, by inspection, which parallel element in this figure has the least conductance? And also find the total conductance of the network and check if your conclusion is correct. Well, since the conductance and the resistance are the reciprocal of each other, right? The element that has the most resistance is R3. So by default, it'll have the least conductance because of reciprocal, right? It has the most resistance, is going to have the least inductance. Just like this one rather, the 2 ohm has the least resistance, is going to have the most conductance. Okay, the reciprocal. So we saw that here, right? So the 1K resistor has the largest resistance, and therefore it's going to have, the most opposition to the flow of current. So if you take the reciprocal of R1, you get 0.5 Siemens. The reciprocal of R2 is what is it? 0.005 Siemens. Let me see something here. The reciprocal of R2, which is R2. I think there's a mistake, a typo in the book. Okay, yeah, because the reciprocal of R2 is, this should be an equal, right? It's 1 over 200, not a plus. Make sure you make that correction. Sorry about that. So the reciprocal of R2 is 1 over R2, and so it's 1 over 200. So the conductance for R2 is 5 millisiemens, and the conductance for R3 is 1 over R3, 1 over 1K, or 1 millisiemens. So the one with the least conductance, which is the 1 millisiemens, corresponds with the one with the largest resistance. Okay. If you add those three together, the three conductances, you get 506 milliseconds. And so if we take the reciprocal of that total conductance, we get the total resistance, or 1.976 ohms. All right, so that's using conductance to find total resistance. But remember, we can also use this equation, right, that we know. We take the reciprocal of the individual resistances, 1 over 2, 1 over 200, 1 over 1K, right, which gives us this result. And then we take the reciprocal of that result, which gives us, again, the total resistance, right, which again is two decimal places. It's the same result. Okay, so make sure you know how to find total resistances using either conductances or the equation of that we have in equation 6.3. Okay, one more before we move on. In this example here, right? When you look at these examples, right, sometimes it's difficult to determine the way they're drawn, what's series and what's parallel. Well, I'm going to give you a couple of hints. The first one is, don't be afraid to redraw the circuit. Okay, as long as you keep the connections consistent, as long as you keep the connections the same, you can redraw the circuit any way you want. Okay, so it'll make sense to you. So don't be afraid to redraw it, but be careful to keep the connections the same. Okay. The other hint that I'm going to give you is that Actually, I'm going to give you 3. That one. You redraw the circuit. The next one I'm going to give you is start from the right. See how we really want to know the resistance looking into these terminals? But always starts from the right side of the circuit, right? And then start analyzing what's connected to what and how they connect it. Well, if you start from the right, you will see the R3 is connected to R2 and is also connected to R3, right, at the bottom. And you notice that also R1, right, is connected to the same point. In other words, this point here at the top connects R1, R2, and R3, right? And this point at the bottom also connects the 3 of them, right? It's the same point. It's the same line. It's the same node connecting the 3 resistances. But it's easier in many cases to start figuring that out if you start from the right of the circuit, okay? And the last clue I'm going to give you, and I think we're going to wait till we haven't really looked into that yet as far as current is concerned, but I'm going to give you a little heads up on that. If you think of a current coming at the top of this connection here, that current is going to split, right? It's going to go, some of it's going to go to R1, some of it's going to go to R2, some of it's going to go to R3. If the current is splitting in 3 ways, then the resistors will be in parallel. Because if the current is not splitting, right? If you think about it in terms of series connector resistance, in a series connector resistance, the current doesn't split. The current is the same. In a series connector resistance, what splits is the voltage, not the current. But in a parallel connected circuit, what splits is the current, not the voltage. And again, we'll have more to say about that in the next few sections, so don't worry about it if you haven't gotten it yet. But you can see that you have different ways of determining whether resistors are connected in series or parallel. So in this case, our assertion is based on how they're connected, right? This point here at the top connects R1, R2, and R3. It's the same connecting point. This node at the bottom connects the other side of R1, R2, and R3. So obviously they're connected in parallel. And then you can proceed using the equation that we already know. Take the reciprocal of each, right, which we did here, and then take the reciprocal of that sum, and that gives us the total resistance, which is about 0.69 ohms. Okay. And as you can see, if you redraw that circuit, right here, if you were to redraw our circuit, in other words, if you move this connection and make it parallel to this one, actually physically parallel, and then you move this resistance down to this side, you get this, right? It's the same connection. It's the same circuit. You didn't change the connecting point. You changed the way the circuit looks, right? But maybe this is a little more obvious for you. So don't be afraid to redraw the circuits as long as you keep the connections consistent, okay? Another clue, another thing that gives you ways of start understanding different ways resistors and devices are connected is by looking at some behavior, right? For example, if you remember when we looked at series connector resistances, when you calculate the total resistance for a series connector resistance, the total resistance is always larger than any individual resistance. Remember that? The total resistance is always larger than any individual resistance in a series connected circuit. Well, in a parallel connected circuit, the total resistance is always less than the value of the smallest resistor. Okay, always less than the value of the smallest resistor. So that's another good thing to remember when you analyze this kind of circuit. The smallest resistance or parallel combination is much smaller than that of the other parallel resistors. The total resistance will be very close to the smallest resistance value. Okay, will be close to the smallest resistance value when you combine them. And that gives you a clue, because if if you check in that rule and is not being and if it's not being checked properly, then you can tell that maybe you did something wrong with the math, or maybe you assume something that may not be in parallel. So make sure you remember these two couple of rules here in blue, and we'll see how we can use them here. Right? For example, just by looking at this example here, right? We have a 3, a 6, and a 100 ohm resistance, all connected in parallel, as we know. Well, without even doing the math, by the time I'm going to calculate the total resistance for these 3 parallel resistors, I can tell that the total resistance is going to be smaller than the smaller resistance. So it's going to be smaller than 3 ohms, right? And it's going to be closer to 3 ohms than to any of the other resistors. See? Without me doing the math, I know that already. And that's a good thing to know, because that's going to lead you to the right solution, and it's going to tell you whether you're in the right path or not. So in this example here, they're asking, what is the effect of adding another resistance of 100 ohm in parallel with the parallel resistors in this example here? So they're saying, okay, what if you take this resistance now and these 3 resistors, and we're going to make an adjustment, and we're going to add another resistor in parallel here, right, for question A. And for question B says, well, what is then, instead of adding 100 ohm resistance, what if we add a 1 ohm resistance, okay, in parallel with the 3 resistors? Well, let's see what the effect is. And you may want to just think about it without doing any math. What do you think is going to happen? Okay, what do you think is going to happen if, first of all, we add another resistance of 100 ohms to this already 3 resistors? What's going to happen to the total resistance? Okay, now what is going to happen now if instead of 100 we add another 1 ohm resistance to the total to the circuit? What's going to happen to the overall total resistance? Okay, you may want to think about it for a minute before looking at the solution, and you should, because that's going to give you an idea what's going to happen, whether you're moving in the right direction or not. So let's look at the solution, right? So first of all, if we apply the equation that we know for the 3 resistors that we have, right? The 3 resistances here, the 3, the 6, and the 100. Remember what we said? Looking at those 3 resistors, when I calculate the total resistance for those 3 resistors, the total resistance will be smaller than 3 ohms and closer to 3 ohms, okay, without me doing the math. So let's see if that's true. So if I take the reciprocals of each, 1 over 3, 1 over 6, 1 over 100, and add the results, and then take the reciprocal, I get my final total resistance is 1.96 ohms, which is what I didn't predict the value, but I knew it was going to be less than 3 ohms and closer to the smallest resistance, in this case, the 3 ohms, right? All right. So it's closer, more like 2 ohms, right? So if we add 100 ohm resistance, okay, let's see what happens. If I add another resistance of 100, right, this is R4. So I'll take the reciprocal of R4, 1 over 100, do the same thing, right? Apply the same rules, and see what I got. I got 0.66 ohms, okay? Oh wait, I'm sorry. This is the 1 ohm they did. Let's see. Well, they didn't do the 100 ohms, but what you'll see first is that if you add 100 ohm resistance, it's not going to change much, because the reason for that is, look at what the 100 ohm is adding to the total value resistance, right? It's adding another 0.010 value to this, so it's not going to change much, right? So at the end, the total resistance is still going to be close to 2 ohms. So the total resistance dropped with the addition of the 100 ohm resistors, but not by much, right? It's just little. However, if we add the 1 ohm resistance, right? If we add that 1 ohm resistance, to the previous three resistors. See what the new resistance is. The total resistance is 0.66 ohms. And see how much it dropped. Why? Because in a parallel connected circuit, right, the parallel connected circuit is going to be closer to the smallest resistance, right? So let's review this again. If we add a 100 ohm resistance, the total resistance is still going to tend to be close to the smallest one, right? So adding the 100 ohm resistance, obviously going to change the total resistance, but it's still going to be a small change because the total resistance is still going to tend to be close to the 3 ohm, right? And we knew that. However, if we add a 1 ohm resistance in parallel, that's going to change a lot more, because now the total resistance is looking at the smallest resistance in that case will be the 1 ohm and not the 3 ohm. So the smallest resistance is going to be 1 ohm, and the total resistance is going to tend to be closer to the 1 ohm. And we see this right here, right? It's 0.66. So you see the difference, right? All right. So the total resistance dropped from 2 to 1.96 in this part, and in adding the 100 ohm resistance. But when we add the 1 ohm resistance, it went to 0.66. Okay. So the total resistance or parallel resistance will always drop as new resistors are added in parallel. It doesn't matter what the value. By how much, it depends. We know it's going to drop, but by how much, it depends on the value. All right. So let's look at now at the special case where the parallel resistors are equal, are the same. Well, that gives us a very useful equation. If you remember, in the case of series connected resistances, when we add resistors of the same value in series, all we got to do is multiply by the number of resistances, the value of the resistance, right? N times the value of the resistance, if they are the same. Special case. In the case of parallel connected circuits or resistors, we're going to divide by the N, by the number of resistors that are the same, right? So for example, in this case here, we have 3 equal 12 ohm resistances. So according to what we already know from the previous equation, what we have to do is just divide one of the resistors by N being 3. So we divide 12, the value of the resistance, by 3, gives us 4 ohms. Okay. Now this is a shortcut, because you can still, if you wanted to, you can still go and say, well, let me take the reciprocal of 1 over 12 plus the reciprocal of 1 over 12 plus the reciprocal of 1 over 12. And then I'm going to take the reciprocal of that sum, and I'm going to get 4 ohms. You're still going to get 4 ohms. So this is really a shortcut, right? Which avoids the the step of having to use that equation, since the values are the same. Just simply take, if they're the same, just take one of the values divided by the number of resistors that have the same value, and that gives you the total resistance. All right. And one more example. In this case, you see this circuit here. And all right, so let's look at this example now. Now you can see this circuit on the left side here. And like I said previously, you can always draw the circuit in a way that makes sense to you. So there's no reason why you can still just work on it the way it is on the left. But if you notice on the right, it's exactly the same circuit. So like I said, if it makes sense to you, redraw it. There's no harm in doing that. At least until you get used to different configurations between series and parallel. But as you can see, these two circuits are exactly the same, right? It's exactly the same. They're all sharing 2 nodes, right? The top node, you see it here. The bottom node, you see it here. It's not so obvious maybe on this one, but make sure you can make that assertion here and just look at the nodes, right? It's important that you understand that part. how to get from the left to the right, being the same. With that said, then, as you can see, it's really a simple problem, because now you have 4 resistors in parallel that have the same value. And as we just saw before, if they all have the same value, all you got to do is pick one of the values and divide by the number of them you have. So in this case, you have 2 ohm resistors, 4 of them. So you divide 2 into 4, and you get the total resistance is a half of an ohm. And it checks, right? Again, it's less than 2 ohms, as it should be. Okay, so now let's look at a really very important short short stop, or a very important way of looking at resistors, especially when you have 2 of them only, because this could give you really a way of analyzing resistors of this kind that it'll expedite things when you do them, right? Well, let's start by just looking at 2 resistors in parallel by themselves, right? And what you have is, when you have 2 resistors in parallel, if you look at the total resistance, again, it'll be 1 over the individual resistance, the addition of that, and then you take the inverse, right? So if you multiply the top and the bottom of each of these terms on the right side by the other resistance result, so in other words, if you multiply this side by R2 over R2, this side by R1 over R1, again, R2 over R2 is 1, R1 over R1 is 1, right? So you're not changing anything. Multiplying that, you get this result, right? And so what this gives you is a shorthand way of getting the total resistance when you have 2, by taking 2 resistors at a time. And what this says is, and it's something that I should really encourage you to memorize it, because you're going to use it from now on. And the nice thing about this is that it doesn't only apply to resistances, but later applies to other things that you learn in AC as well. So remember this. If you have 2 resistors in parallel, the total resistance for the 2 is the product of the individual resistance divided by the sum. Again, the total resistance for 2 resistors in parallel is equal to the product divided by the sum. That's it. So if you look at, for example, let's look at this one. We use it. Example 6.8, right? You have these 2 resistors, and they want to know the total resistance for this parallel combination. Okay. Is this one? No, they're referring to figure 6.7. So let's go back to figure 6.7. All right, it's figure 6.7. All right. So let's see. Let's just see what they want to do here. Okay, so they're saying, all right, let's look at this figure. And let's find the total resistance, which we already did, right? Using the long way, if you will. And now we're going to use this shorthand or shortcut method. So what they're going to do is they're going to take 2 of those resistances. It could be any of the 2. But they're going to take 2 of them and combine them into 1, right? So they're going to take the 1 and the 4, right? Combining into 1 resistance. And then they'll have, think about this, if you combine these 2 into a single resistance, right? Then you ended up with 2 resistors in parallel. The combination of these 2 and this 5 ohm. And then you can apply that rule again, right? And that's the beauty of this thing. And you'll see how this works in the example. So remember this, right? You have the 1, the 4, and the 5. And you're going to combine them. All right, so we have this problem, right? It says determine the total resistance for the parallel combination of the previous figure, right? And we have the 1 and the 4, so, and the 5 here. So if we combine the 1 and the 4 using this previous method that we explained, you have a 1 and a 4, right? So we're going to take the product of 1 and 4 divided by the sum in 1 and 4, so you get 4 over 5, right? The product divided by the sum. So you get 4 over 5 is 0.8. So now in this intermediate step, you have combined the two first resistors, right, into this 0.8 ohm resistance, and now you have two resistances. So you can reapply the same rule. And if we reapply the same rule, we say we're going to multiply 0.8 times 5, and we're going to sum 5 plus 0.8. So again, 0.8 times 5 divided by 0.8 plus 5 gives you 5.8 for a result of a total resistance of 0.69, right? Which is the same result we got before. But the nice thing about this is that you don't have to do any reciprocals. You don't have to keep track of, taking the reciprocal of resistance and then taking the reciprocal of the whole result. This gives you the result directly, okay? So it's really a shortcut method that is really, really important that you learn it and you know how to apply it, okay? Because it applies to circuits that may have parallel resistance, many parallel resistance, but as long as you apply it two at a time, like in this example, you're fine. Another thing that we learn is, if you remember in the series connected resistances, we can exchange resistors from location to location as long as they remain in series. We can do the same thing with parallel resistors. We can exchange or interchange where they are without affecting the total resistance. And this is one example of this, right? We have 5 resistors here, as you can see, and we could move the 6s together and the 9 and the 6 on the side, right? By doing this, by moving those resistors in that way, interchanging them, it's not going to change the total resistance. The total resistance is not going to change. You should be careful when you do that, because if you're looking for something specific to those resistors, then you have to follow what the resistor is. But as far as the total resistance, it's not going to change it, okay? And so if we do this, and you don't even have to redraw it, you don't even have to bring them together, but this shows you a more systematic way of doing that. But in this case, they want to combine the 6s together, and then they just brought them into this new circuit. You don't have to do that step, but if that makes it clear, that's okay. So if you combine the 3 resistors of the same value, the 6, then if we apply the rule, remember, what we have to do is divide that 6 resistance into 3, because there are 3 of them, and that gives you a 2 ohm resistance. So if you think about it, these 3 resistors can be combined into a single resistance that is of value 2 ohm. So the 2 ohm resistance replaces those 3. And now you will have a 2, a 9, and a 72 in parallel, right? Well, you can also go, 2 resistance at a time and combine the 9 and the 72, right? So, and use the shortcut notation. By combining the 9 and the 2, we multiply 9 times 72 over 81, right? Not the product over the sum. And that gives you an 8 ohm resistance. So what you have now by doing that is you have this 3 resistors combined in parallel to give you a 2 ohm resistance, and parallel with this combination of a 9 and a 72, which gives you a 8 ohm resistance. And now you have a 2 ohm in parallel with a 8 ohm, and you reapply the rule again, because now you have 2 of them. So you have a 2 and an 8 combined, right? So you have 2 times 8 divided by 2 plus 8, and it gives you a total resistance of 1.6. All right? Okay. So you see how easy that is, right? Let's look at another example here. This is sort of looking at the method, but using it to find an unknown resistance in the case you know the total resistance, right? Well, the same idea applies, right? Because if you look at this example, they're giving you the total resistance, they're giving you the value of one of those resistances, but they want to know what the unknown is. Well, if we apply the rule that we just explained for 2 resistors, you'll have the product over the sum will be equal to the resistance, right? The product over the sum is equal to the total resistance. In this case, we know the total resistance, and we know one of those resistors, which is R1. So there's an unknown R2. So if we can combine this equation and solve for that unknown, right? In other words, if you take this equation, multiply both sides by R1 plus R2. If you multiply this right-hand side by R1 over R plus R2, rather, that cancels at the bottom. And if you multiply by R1 plus R2 on the other side, you get this expression, right? So that's what happens when you multiply both sides by the bottom here. And if you combine, right, combine the terms, multiply, bring this term over the right-hand side, right? It's positive here is going to be negative here, right? Because remember, you're solving for R2. That's what you want to find out because you know RT and R1. Well, if we do a couple more steps, you see how easy it is. You're just solving for R2. So R2 is just this expression. And you know the values already. Right? So just substitute and find out that R2 is equal to 36 kilo ohms. Again, if for any reason you find out that R2 is less than less than 12 kilo ohms, or rather less than 9 kilo ohms, I should say, then something is wrong, right? Because no resistance is going to be less than the total resistance in a series combined case, right? So that's a check. Okay. Well, the example, I'm going to leave you to solve this one on your own, study it and make sure you understand it. It's applying the same concepts. Something we have done in the lab as far as measuring resistance, but you can see here how it's done for a pilot combination. It'll be the same sort of applications. In this case, if you want to know the total resistance, you apply an ohm meter across, the combined resistances, like in this case, and that's how you will get it. All right, so now that we know how to combine resistors in parallel, how to manipulate them, we can then add a source, and then we have a circuit, right? So what's particular about parallel resistances, going back again as a reference, with series resistance, remember, in a series connected circuit, the current remains the same, but the voltage splits, right? You know that, right? Well, in a parallel connected circuit, the voltages across the elements remains the same. It's the same, right? But the current splits, right? And you can see that in this picture. Why is it the same voltage? Well, if you look at this circuit, right, the resistances and the voltage source, they're all connected to the same two nodes, right? The top is connected to node A, the bottom is connected to node B. So there's nothing in between, this connection at this end, this connection in the middle, this connection on the side is the same node, right? It's like different points in a protoboard for the same node, right? For the same connecting point. So there's no drops. This is ideal, of course. So there's no drops, right? So the voltages remain the same, as you can see, right? So the voltage for parallel connected resistances is always the same. But as you can see, if you look at the current coming out of the source, IS, that current, some of it is going to go across R1, some of it is going to go across R2. So the current splits. Okay? Compare that again to what I just mentioned about series connected circuits. Now, just like we said in the series case, you got to be careful because if two elements are in parallel, the voltage across them are going to be the same. The voltage is going to be the same. However, if the voltage across two neighboring elements is the same, it doesn't mean that necessarily in parallel. Okay? Just keep that rule in mind. So if you already know they're in parallel, then you can assume the voltages are the same. But if the voltages are the same, you cannot assume immediately that they are in parallel. They might be, but they may not be. Okay? Just like in the circuit, in the series connected case with current, right, that we mentioned before. All right. So, okay. So we can see now that if you look at this circuit, for example, and if you want to know what the source current is, well, you will first have to find the total resistance, right? In this case, there's two connected in parallel, so it'll be the product over the sum, 3 over 4, or 0.75 kilo ohms, and then you have a very easy circuit. Use Ohm's law, which will give you the current equal to 12 volts divided by 0.75 kilo ohms, right? Very easy to do. Now, since the voltage is the same across each of the elements, then you can find the individual currents, right, for each of the for each of the resistors by using Ohm's law as well. Because in the case of R1, the voltage across R1 is 12. So the current will be 12 into 1, 12 divided into 1, or 12 milliamps. And the current, the voltage across R2 is 12 volts as well. So the current I2 is going to be 12 divided into 3, or 4 milliamps, kilo ohms. Because this is kilo ohms, it'll be 4 milliamps. So we said this is 1, right? And this is 4. And just like we found out, right, that the case of the total resistance will be the voltage across the elements divided by the total resistance. But then you can individually find those currents as well. All right. So the other thing to remember again is that, as I mentioned before, the source current in series parallel connections like this, right? If there's nothing in between here, like in this case, it's only a wire, right? The current splits, right, into two currents. So the source current will be equal to the sum of I1 and I2, right? Which is this expression here. All right. And again, this reminds you of what I mentioned just a few minutes ago, that for parallel connected circuits, the source current equals the sum of the branch currents, right? This is called the branch currents. While for a series connected circuit, the applied voltage is the sum of the voltage drops, right? So in a series connected circuit, is the voltage that splits, but the current is the same. So you can see for a parallel connected circuit is the current that splits, but the voltage is the same across each of the elements. This is really, really important that you remember this. And not only that you remember it, but you understand it, okay? It's important that you understand this figure. Make sure you do. Study it. Okay, so let's look at one example here. Another example, this circuit, and they want to know the total resistance, the source current, the current through each of the branches or through each of the resistors, and we want to show that this equation here is satisfied. All right, so we know what we're going to do, right? You're going to combine these two resistors. To find the total resistance, we're going to multiply 9 times 8 over 18 plus 9, right? That will be the total resistance. So the total resistance is the product over the sum, 9 times 18, divided by 9 plus 18. And that gives you a total resistance of 6 ohms. Okay? Now it says find the source current. Well, since the voltage is 27 volts, if we divide by the total resistance, it gives us a source current of 4.5 amps. All right, no problem. And then if you want to know what the individual currents or the branch currents are, well, we have 27 volts across R1, we have 27 volts across R2. So I1 will be 27 divided into 9, and I2 will be 27 divided into 18. Right here, 27 into 9 gives us 3 amps, 27 into 18 gives us 1.5 amps. And if we add those two together, we should have the total current again that is being sourced, which is 4.5 amps. So it checks. All right, I'm going to leave this one again for you to study, this example, and make sure you can follow it and understand it. If not, let me know. Another one of those rules to remember is that for parallel resistors, the greatest current will exist in the branch with the least resistance. And that kind of makes sense, right? Because because of the resistance current combination, right? Resistance and current are inversely proportional, right? Remember Ohm's law. And which is another way of saying that current always seeks the path of least resistance, right? It's always gonna go, most of the current is gonna go where it sees the lesser resistance, right? It's another, it's really another product or another result of really thinking about Ohm's law and the combination, the relationship rather, between current and voltage, current and resistance in under Ohm's law. They're inversely proportional, right? Think about that. Think about Ohm's law and how that really makes sense when you look at these two statements in blue, right? All right, let's look at this problem now. And this problem says find the value of R3, find the applied voltage, and find the source current, and find I2 as well. Well, if you study the circuit for just a little bit, right, it's always a good idea to first kind of look at the circuit for a few seconds, for a minute, or a couple of minutes, whatever is needed. So just to understand what you are given and what is it that you're looking for, right? And kind of come up with a strategy before you actually start writing things down and lose perspective. Because it says, well, find R3, and if you look at the circuit, you say, well, I don't know R3, but what do I know? Well, I know the value of R1, I know the value of R2, and I know the total resistance. So really, you know, if you combine the resistors together, the only thing I wouldn't know in that equation will be R3, right? So I can find R3 based on the equation for total resistance, right? And the other thing is, if you look at the circuit, they're also giving you the current through one of those resistors, which is this one, right? The 10 ohm resistance. And they're not giving you the other ones. But however, by Ohm's law, you can find the voltage across R1, wouldn't you? It's just the product, right? 4 times 10, the voltage by Ohm's law. So that's 40 volts. But what do you know? Well, you know that the voltage across each of those resistors is the same because they're in parallel. And that voltage is the same as the source voltage. So right there, you know the voltage. And if you know the voltage, you know this current, right? So get into the habit of kind of solving the problem in your head, just like I did here, without you know, coming up with any numbers. Just word it out and come up with how you're gonna find that. Because now all you have to do is really plug in the numbers, and then you have a solution. So we said to find R3, we're gonna use the total resistance equation, right? Which will be, you know, the individual resistance. Which, by the way, you can use the shorthand case, but let's just follow the way they do it in this example, because you can use that shorthand way also. You know, by combining these two times 10 times 20 over 10 plus 20 gives you this, and then you recombine it again with R3 and solve for R3. You'll get the same result. But in this case, they use the long way of doing it with this equation, right? So 1 over R1 plus 1 over R2 plus 1 over R3, and then we take the reciprocal of that. However, we know 1 over RT, right? Because we know RT, but we don't know R3 in this equation, right? From this expression, we don't know R3, but we can substitute for the other numbers as they did here, and then solve for R3, right? So you solve for R3, and R3 is equal to 10 ohms, right? So you can see that R3 is given by looking at the total resistance expression. And then from Ohm's law, like I said before, if you look at this resistance, right, by Ohm's law, it's just the product of the current in the resistance. So it's just 4 amps times 20 ohms, 10 ohms rather, which gives you 40 volts. And the source current is then, since you know that this voltage is the same as the source voltage, all the voltages are the same across each of the elements, that gives you the total current as 40 volts divided by 4 ohms or 10 amps. And then from that, you know, well, what else? I2. But I2 is also the same voltage, right? Which is, we said, is 40 volts divided by 20 ohms, and it's 2 amps. By the way, you notice that we found this source current to be 10 amps, right? And we already given what is it? The source current is 10. Yeah, the source current is 10 amps. Then I'm looking to find. Then what if you wanted to find the current across or through R3? Well, if you notice here, the source current is 10 amps, right? We found this current to be what? I2 is 2 amps, right? So this is 2 amps, this is 4, right? And this is 10. But remember, these 10 amps are going to split among R1, R2, and R3. But this is 4 and this is 2. So this gives you a total of 6 between these two. So that means that another 4 go through R3, right? Because you will now have 4 plus 2, what is it? Yeah, 6 plus 4 equal to 10, which is the current that comes in, right? Check that out. Make sure it makes sense, right? Find the current through R3 by just looking at the individual, sum of the currents. They should be equal to the total current. All right. And just another look at how would you do this in the lab, right? And what would you read or what would you measure? And it'll make sense, right, that if you have two resistors in parallel and if you measure the voltage across each of them, you're getting the same voltage. The only difference here is that they swap the, I guess, no, they didn't. They're just swapping the leads, but you still get the voltages that you get here. So just notice that in here, the top one is voltage and the bottom is telling you what the current is. So in this example, you will measure the same voltages, right? Same thing here. If you want to measure current, you will put the meter, remember, in series now, right? Make sure you understand this, right? You place in the meter in series with the source, right? You're inserting the meter. For example, if you look at this problem here, right? Think of what you have in that picture. You will put the meter right around here in series to measure the current, right here, measuring current. And that's what they've done here. To measure the current, they put it in between the voltage source and one of the connecting points, right? So important you understand that too, okay? For the lab portion as well. All right, let's see. What else? We're going to talk later about what an open circuit is, so it'll make more sense, as you'll see. But in this one also, see how they're measuring current across resistance R1. Again, they're putting the resistance and the meter in series because they're measuring current, right? Again, make sure this makes sense to you because this is what you need to do in the lab. It's really important. All right, so before I break for this lecture, let's talk about power distribution in a parallel circuit. And as you will see, is very similar to what you do in the series connected circuits. Okay, but it goes like this: for any network that you have different resistive components, like in this case, the power that is being applied by the source is going to be equal or to the addition of the individual dissipated power by each of the resistances, right? So if this is the power flow, the power absorbed by these resistors, when you add them together, it's going to be equal to the power being supplied by the source. And that's what this equation says. And really, if you look at it back in the series connected case, it's the same idea, right? Because conservation of power. the power being absorbed by the individual resistors, adding them all together has to be equal to the power being supplied by the source, right? Same thing as in the series combination. The difference, and you gotta be careful, is how you obtain that power, okay? You gotta be careful with that idea. But as far as power is concerned, it distributes in the same way that it does in the series combination, okay? And you can use the same equations as before, right? The voltage times the current, or you can use the square of the current or the square of the voltage to find that power. It's the same equation. That doesn't change. All right. So let's look at one example here. In this one, this circuit here, we want to find total resistance. We want to find the source current and the current through each resistor, the power delivered by the source, and the power absorbed by each of the resistors. Again, come up with a strategy, right, before you start working on the problem. Look at what is given. Look at what is it that you're looking for, they want to find that. The first thing they want to know is find the total resistance. Well, what's going to be my approach to finding the total resistance? What equations do I know that will help me find the total resistance? Well, you can go the long way, right? And take 1 over R1 plus 1 over R2 plus 1 over R3, and then take the inverse again, the reciprocal, to find the total resistance. That's fine. Or you can combine 2 of those at a time. Which ones you combine doesn't matter at the end. But let's say you combine the 20 and the 56, right? You go 20 times 56 over 76, and that result you combine with a 1.6 using the 2 resistor formula, and that gives you the total resistance. So right there I know what to do. And it says find the source current. Well, it's easy now, because if you know the total resistance, use Ohm's law. It'll be 28 volts divided by the total resistance. That gives me the source current. Now it says find or calculate the power delivered by the source. Well, again, power is going to be voltage times total current. In this case, since you find in step B, you find the total current or the source current times 28 gives you the power, right, being provided by the source. And then for the individual powers, you can use either I square R or V square over R. Because you know, well, you don't really know I1, but you can find it, but you really know V1, V2, and V3 are the same, so it'd be easier to just use V squared over R in each case, right? See? And again, I already really solved the problem in my head without really having to put any numbers in it. So again, get used to that, that approach. It's going to help you a long way. Okay, it may take you a while, but just just practice it. But now we know what to do, right? So to find the total resistance, I want to use 1 over R1 plus 1 over R2 plus 1 over R3, and then I'm going to take the reciprocal of that, right? And there you go. It's 1.44 kilo ohms, right? It's really just a math little problem. To find the source current, again, since I know the total resistance, it's just 28 divided into 1.44 kilo ohms, and that's your total or source current. And to find the power delivered by the source, let's see, how did they do it here? Oh, they just found the individual currents, and that's fine. Did they ask you for that? Oh yeah, the current through each resistor. Well, no problem, right? Because the current through each resistor should be 28 divided by 1.6, 28 divided by 20, 28 divided by 56, right? Because it's the same voltage across each resistance. It's right here, 28 divided by each of the individual resistors gives you each of the currents. And again, as we saw, that the power delivered by the source is equal to the voltage times the source current, and then you have the source power. And if we can use any of the equations now, since we know the currents and we know the voltages across each resistance. See how they use the 3 different equations, right, to find each of the power absorbed by the resistances. And this is a nice exercise for you, so that you know that you can use any of the equations. As long as you know one or the other, voltage or current, you can find any of those equations to find individual power being absorbed. And if you add them all together, you're getting the source power, the power being delivered by the source. So it checks, right? Conservation of power. All right, so I'm going to stop right here. And in the next lecture, we're going to continue by looking at Kirchhoff's current law. Just like we have a Kirchhoff's voltage law for series connected circuits, we also have a Kirchhoff's current law for parallel connected circuits.